Okay.
Yes, live.
Well, thank you, Dmitry, for giving us a bit of your time. And the idea is just to have an informal chat about information security. And it came to me that I heard about gophers, this tool that you have developed, and I thought it would fit the theme of information security when it comes to automated testing. So could you please let us know a bit more about you for people who don't know yet who you are? Dmitry?
Hi, my name is Dmitry Vyukov. I work for Google in Munich as a software engineer. My main team is dynamic testing tools, and we're working on tools called address sanitizer, thread sanitizer, and memory sanitizer, which are now part of both GCC and Clang, and they find all kinds of nasty stuff in C and C++ programs. Also, I work on the Go language, mostly on the runtime, and also I work on the dynamic tools for Go as well.
Okay. Some of the other guys here online, there's Alex, hi, Frederick, and Nicolas.
Hi.
And Valentin is not able to chat with us. He's not equipped, but he'll be maybe chatting with us with his keyboard.
Yes, I'm gonna read his messages if you don't mind.
So basically, next week we
had some nice, interesting questions.
We're organizing a meetup themed on information security with the Golang meetup interest group in Paris. And just before this session, we'll be having discussed the activities of two companies, Centrio and TrustLM. And right now, maybe we could hear a bit more on gophers, if you would like to tell us a bit about it, or unless there's a hot topic you'd like to chat about. I don't know, it's up to you, Dmitry.
Can you hear us, Dmitry?
Am I still being audible or heard? Hello, Dmitry, are you with us?
Yes, I'm with you, but audio quality is not very well.
Oh, okay.
Could you repeat the question?
Right. I don't know how, guys, you're planning to organize this session, but maybe a starting point would be to chat about, to discover what gophers does, where does it come from, what was the motivation, and what is it useful for?
Okay. So go-fuzz is a fuzzing system, fuzzing is randomized testing. My team created some tools for fuzzing of C++, and I thought that it's pity that Go doesn't have any fuzzing solution. So in the native land, it's quite well-known technique for security testing, but there is nothing for Go. So I decided to write a fuzzer system for Go. So I have a small presentation which I would like to show and tell along the way. 1 second. Do you see the presentation?
Yes.
Yeah, perfect.
The code is well tested.
Okay, great. So you probably have unit tests and hopefully maybe even system tests and maybe even integration and stress tests. But if you have a large complex piece of code, what amount of tests will make you sure that it's correct? And this is a good question. And it turns out that normal testing techniques don't find all bugs in the code.
Mm-hmm.
And so the the technique that I want to introduce is randomized testing. And the idea is very simple. We just generate a random blob of data and feed it into the program and see if it crashes or anything bad happens. So it's very cheap to use because you don't actually need to write any tests. And another good thing is that this technique doesn't have any bias, and lots of bugs are overlooked because programmer has some bias and thinks that some piece of code like must be correct and just don't code. And this does find real bugs, but in this simple form, it's not very efficient. So the question is, how can we generate diverse but meaningful inputs that will actually find nasty things in our code, like crashes or infinite loops or some correctness corner cases.
Mm-hmm.
And here comes the technique called coverage-guided fuzzing. So it's essentially a genetic algorithm, and the idea is as follows. So we have some initial corpus of inputs for the program. We can take it just from unit tests. Then we randomly choose one input from this corpus and randomly mutate it. For example, flip a bit or insert a byte or remove a byte. And then we execute this input on the program and collect coverage. And by coverage, I mean the same coverage that you get with go-to cover. It's just source code coverage. So if this input gives some new coverage, so it covers some lines of code that are not covered by any other inputs in the corpus, then we add this input to the corpus and repeat from the beginning. So this technique basically incrementally digs deeper and deeper into your code, and it can easily crack piece of code that you see at the bottom. So we'll just guess input bytes one by one, add those inputs to the corpus, and so on. Okay, so this is roughly how most of the coverage-guided fuzzers work. For example, the American fuzzy loop for native code. But go-fuzz has some secret sauce inside. So let's consider this piece of code. This is taken from the standard library from the image PNG parser. The parser calculates checksum of the data and then compares it with the checksum contained within the file. And this is kind of game over for traditional coverage-guided fuzzers, because the probability that the random mutations will generate some interesting new input and at the same time guess the 4-byte checksum is basically never. It just doesn't happen at all. And to solve this issue, I've added a piece of code that I called Sonar, and it works as follows. So the insight was that we don't actually need to guess the checksum because the program already knows it, and we have a program instrumentation for coverage. So just need to add a piece of slightly different instrumentation, and it's shown on the slide. We intercept the values being used in comparison operations and pass them to the runtime library. Runtime library collects them and makes them available to the fuzzer. Fuzzer does the following. It sees that value 1 was compared with value 2. It finds value 1 in input data and just replaces it with value 2. And that's it. We're guessed the checksum in basically no time. It's just taken it from the program itself. And if you look at the code, it actually compares the big Indian representation of the checksum. So the bytes in the input are reversed, and Sonar can understand this. It also searches for the reversed version of the value, and if it finds reversed version of value 1, it replaces it with reversed version of value 2. So it still works, and it understands some other encodings like base 128, hex, ASCII encodings, and so on. So this allowed to break the image PNG code and actually find much more bugs than the fuzzer was able to find before I added this technology. And then there is another technology that complements Sonar. So mutations in Sonar do only low-level changes like bit or byte flipping, so to say. But if we have something more complex like XML, the input that mutation can produce is, as you can see here, like remove slash. That's maybe also interesting input for the XML parser, but for this input we actually want to do higher level changes. And to support that, I implemented the thing called versifier, and what it does is it tries to reverse engineer text protocol and learn its structure. So, for example, if it sees a sequence of digits, it understands that it's a number. If it sees something in quotes, it can understand that it's like something in quotes. And the same for lists and key value pairs. Also, it looks at new lines, because new lines in text protocols usually mean serve as some kind of a structuring element. And at the bottom you can see the inputs that versifier was able to generate. Oh, sorry. So after learning the structure, versifier can apply structural mutations to this input. For example, if it sees a list, it can add like another element to the list. Or if it sees a number, it can replace it with completely different number, and so on. So at the bottom, you can see some of the inputs that it generated from the original XML, and I've tested that those inputs are all valid XML, so they passed through the XML parser successfully. You can see some weird things here, like it added nested item elements and it duplicated the prop sub-element and so on. And both Sonar and versifier doesn't just generate new interesting inputs, they also amplify effect of the mutation part, because they work in the same closed coverage guided loop. And you can see the overall structure of how the go-fuzz roughly operates. So we start with the corpus, and then choose to either mutate one of the inputs or versify one of the inputs. Then we execute this input. So if it crashes, then great, we find a new crasher. We just remember it. If there is no new coverage, then we usually just discard the input, but sometimes we pass it to Sonar. For example, if there is incorrect, if we did some interesting mutation but didn't guess the checksum, Sonar will patch the checksum and execute the same input but with the patched checksum. And if there is new coverage, then we first minimize the input to the minimal form that gives the same new coverage. And then we do what I call smash. Smash is some mandatory program of attention for each new input. it tries to flip every bit one by one, then flip every byte one by one, then try to replace every byte with some set of special values like 0, tries to trim the input after every byte, and so on. Then it's also passed to Sonar, and then it's added back to corpus, and the loop closes. And this all works in parallel and just infinitely generates something new. So I have a quick quiz for you. Here's a list of standard packages, and the question is, in which of the following standard packages go-fuzz did not discover a bug?
None.
None. It's a wrong answer.
Ah.
Time?
Wrong. That's exactly one package in this list.
Well, PNG or GIF? No?
PNG, GIF, no, wrong.
Regex.
What?
Regular expressions.
No.
It's FMT probably, because it's supposed to be the most tested one.
Sorry, I can't hear you.
FMT? FMT?
No, wrong.
I would expect at least that to be tested. This is like one of the most used packages.
Okay, so the correct answer is image SVG because it does not exist.
So none.
we all felt in the classical trap in every QCM.
I've applied go-fuzz to the standard library and some other packages, and in about 2 months I found more than 100 bugs in standard library, which is probably the most well-tested Go code out there, and 32 bugs in various Golang.org/x packages, and more than 100 of bugs in other packages. So here are some interesting examples. So you try to name formed. So if you try to form this string, it will panic. And you also name regex. So if you try to compile this regex, it will also crash with out of bounds. And the time also turned out to have some issues. For example, it's possible to specify signs before year and minutes in time zone, which is usually disallowed. So the template package, it has lots of bugs. It's easy to crash it or turn into infinite loop. And then the flate package, that was quite interesting bug. So if you try to deflate those particular 10 bytes, it will just hang forever. And the flate package is used in HTTP compression, right? So it's possible to send the 10 bytes to a server, and it will just burn CPU forever, and you pay thousands of dollars to cloud hosting. And so there was all kinds of bugs like crashes, panics, consumption of gigabytes of memory, and so on. Okay, so the usage of go-fuzz is very simple. You go get go-fuzz, then you write a test, which is quite simple. You can see complete example here. So this is a test for Gopen decoder. It just accepts the blob of data from fuzzer and tries to decode it. Then you build this with a special go-fuzz build thing, which does the instrumentation magic. Then you collect some initial corpus, and then you run go-fuzz, and it just runs and collects crashing inputs in a directory. So that's it for the presentation.
Mm-hmm.
And now I can answer any questions.
Okay.
I have some. Thanks. It's very interesting. First question: how is it different from the package testing/quick, which is in the standard library?
Mm-hmm. So that testing/quick just blindly generates random inputs. It is not like coverage guided thing. So there is no chance of guessing not just checksum, but also something that requires, you know, a series of primitives mutations. Like, for example, I don't think that it can generate add a new element or XML input or something like this.
Yeah, understood. There is no heuristic.
Yes, it's very, very trivial.
Okay, and is it similar to what SQLite does? Because SQLite is very well known for having a very strong test suite, which is based on pushing random things into the SQLite engine, and many specialists attribute the lack of bugs in SQLite to this technique. Is go-fuzzing a similar idea?
I actually don't know how that corpus for SQLite was collected.
Yeah, okay.
I can answer this question. So that there are coverage-guided systems for C++. So if I would work on SQLite, I would use that to collect like a good corpus of inputs.
Okay.
I'm just curious. Right now, gophers is measuring failure. I mean, discovery of a bug by detecting if a program has crashed. Sometimes you might want to detect if the program is running slower, for instance, because I think in the Golang world, one thing that appeared in this language is the ability to create many Go routines as you want or very easily. And a side effect of that is that you may run into situations where a bug might generate the creation of many Go routines, some like Go routine leaks. Have you thought of this avenue of exploring bugs that induce Go routine leaks? Or?
So it's in the fuzz function, it's possible to detect any kind of error conditions and just panic on that. For example, you obviously can test for correctness. For example, in the deserialization tests, I usually deserialize data, then serialize again, and then deserialize again, and then compare results of deserialization. And if they differ, I panic. Also, in some tests, I had to check for a number of Go routines in the program, and if it's, say, higher than 50, then you panic. And in the panic message, you will actually see all the stacks of the Go routine. And I found the bug in the text template package this way. So if you give text template an incorrect template, it will return you an error, but the background parsing Go routine hangs forever. So it's possible to detect that kind of bugs. And also, obviously, driver checks for timeout. So if a program just hangs on a particular input or takes minutes, then it will also detect that.
Okay.
I have a question. So you said the go-fuzz uses a genetic algorithm to generate random mutations and test different inputs. How long? So I'm guessing there are different generations of inputs that you test, and then you have a loop, like an infinite loop I'm guessing, of inputs and testing and inputs and testing. Suppose you don't detect anything for 10 generations. How long does it have like a stop period where you say, okay, I think the program is fine, or just decide by yourself when, okay, I waited 30 minutes, nothing happened, so I guess my program is fine. I just how exactly does it stop? Do you always find bugs?
So it's a good question. So the go-fuzz doesn't stop. It's your decision. It gives you some statistics as to when it detected the last bug and generated the last interesting input, the last new input, and then you decide. So I would suggest to run it, like, leave it overnight, at least.
Okay.
So there is no definitive answer to this question.
Okay, cool. I haven't actually looked at go-fuzz, the exact implementation of the genetic algorithm, but usually in the machine learning world, like the genetic algorithms are kind of slow to converge to some sort of expected output, or to match a given training set or something like that. And do you think there's like an advantage of using just the genetic algorithm, or you think some other sort of generating different inputs might be like for using a different kind of mutation strategy?
Do you ask about different kinds of mutations, or completely different algorithms?
Like if you just try random, as you said, like in the image PNG package, it's very difficult to know if you just do a random brute force on the input, you might not have the failure, the expected failure kind of, because it just repeats the same kind of input. So you have this analysis of different type, and so I guess my question is like, do you envision having a different kind of heuristic other than doing random mutations on the? I don't know if I'm explaining it.
So I do different kinds of things, and that's sonar technology and versifier, which are radically different from just random mutations. And they're super useful. So they just find new inputs by themselves, and also like add to the corpus and give the random mutation part more work. Another idea that I didn't yet explore is that you can write a generator for inputs, like on your own, just explicitly, and plug this into go-fuzz, and it will, for example, it will do 10 random mutations and then ask your generator for some new input and execute it as well. And also, it will also be plugged into the coverage guided loop, so go-fuzz will actually be able to filter the interesting inputs from the generator and add them to the corpus as well. So yeah, I would say any such addition is very useful.
So it's like a hint for the corpus. I think Valentin is asking more. Your mic is a bit quiet. Okay. Okay.
Okay.
I think I don't have any questions.
Maybe I have a very general question. What do you mean by Go dynamic tools? I saw it was the title of your presentation.
So this was a part of a larger presentation, which also includes data race detector and execution tracer.
Okay, I see.
Dmitry, is there a usual type of error that you see quite often. Behind this question, there is another question asked by, as a reminder, I asked a few people, some members of the group, if they wanted to ask you questions, and someone came up with the question: are there any good programming practices to enforce solid code or robust code in Golang? So, do you have any tips or advice for the programmers who work with Go on things to avoid or things to make sure? Or is there a common, very usual type of error that you see quite often?
Nothing comes to mind. So most of the errors were, there were lots of different types of errors. It's not that there's like only one.
Okay.
Like go-fuzz just found lots of like classical bugs like off by one checks or missed error checks. Like assumptions about input data that are not necessarily true, and so on.
Okay.
So I don't know. So the suggestion would be to use go-fuzz for testing.
Right. Someone also came to me with more general questions on the latest new tools that appear, and someone was asking me if you or Google have an idea or an opinion on the tool made by, if I'm right, by Dave Cheney called GB, the build tool.
I haven't tried it yet, so I don't have an opinion. I don't know. So I usually work on quite simple projects, and Go tool works just fine.
Okay. All right. Well,
maybe a more general question, because I think that most of us work on web applications that are connected to the internet. And if I understand what gophers does, it only works on a slice of bytes. Yeah, is it correct? Yeah. Okay. So it means gophers to be useful. I need an application that accepts a slice of byte as an input.
Yes. Yes, there is such issue. So in some tests, what I did is I split this byte slice into several strings. For example, in the regex package, I just split this input into two pieces and use the first piece as the regex and the second piece as a string to match. So it's possible to do, such transformation. For example, if you need an int, you can take, say, first byte of the input and use that as an int.
Okay.
But for now, go-fuzz doesn't do anything automatically. It may be possible to, for example, use some simple serialization format like GOP or JSON, and then accept that JSON and then deserialize into the your structure that your program, your function needs, and then use deserialized object as input.
Okay, that's very clear.
Yeah, probably there is. It's possible to provide some support for such cases when you need something more complex than just byte slice, but I haven't done this yet.
Yeah, the same approach could be expanded by using maybe the Reflect API and try to understand the data structure and mutate with the exact same general algorithm with mutations. But obviously, it would be difficult probably to implement.
Yes, it's possible to do. Yes, I haven't tried to implement it yet. So I've tested things like deserialization, compression, images, image parsing, audio parsing.
Okay.
I don't know, like certificates and HTTP input, which is also just a string. Yes, I think it's possible. I don't know. If somebody is willing to contribute, I will be happy to accept that.
I think Valentin has a question. Can you see it, Dmitry?
No, I don't see the chat.
Okay.
He says, I can read it. He says,
Oh,
I have one specific question about stack traces. Can you hear me well? Can you guys hear me well?
I'm reading the question. 1 second.
Okay. So he says, are stack traces useful for other purpose than debugging in Golang? So if the Go compiler wanted to implement the so-called tail recursion, we would probably lose some lines of stack traces. Would it be a problem? That's Valentine's question. I can repeat it if you. So are stack traces useful for anything other than the debugging in Go?
Stack traces. So the go-fuzz uses source coverage, but it's actually possible to use any other metric. For example, in native land, fuzzers frequently use so-called edge coverage. It's if you have a branch, they see whether you go into one direction or in another. It's also possible to build more complex metrics. For example, that you not just execute this particular function, but that you execute this particular function from that other function or from a different function. And this connects us to the stack traces. So it may be possible to introduce some notion of like stack coverage that will actually examine different call chains. For example, if this input triggers a call chain that is not triggered by any other input, then it's also potentially interesting input. So yes, stack traces can be useful in this context. But I think that there is a strong desire in the Go team to preserve stack traces, and that's one of the reasons why we don't have tail recursion. And this also limits inlining possibilities to some degree, but it's actually solvable with debug info. So I would say that we can rely on the fact that stack traces will be preserved by Go implementation.
All right.
Does it answer the question?
Valentin?
I guess we have to ask Valentin.
He's typing now, I guess.
He doesn't have any.
Well, well, thanks a lot for your time, Dmitry. It's been very interesting. Lots of work for us to get acquainted with gophers. I'm gonna have to look at it soon when I find time. And you're off to the GopherCon next week or this weekend?
Yes, this weekend. So you're welcome, yeah, and please try go-fuzz. It should be simple, and if not, then report.
Report bugs.
Okay.
Thanks a lot, Dmitry. It was very interesting.
Okay.
You're welcome. Thanks for the interesting questions.
Is it a typical Russian dacha behind you on the wall?
Sorry?
Is it a typical Russian dacha behind you on the wall?
No, I'm actually in Munich, in Munich Google office.
Okay.
I don't know what it is.
It looks like a dacha. Спасибо, до свидания.
Пожалуйста. До свидания.
Okay. Thank you. Bye, everyone.
Bye, guys.
Bye. Thanks, Fred.
Ciao.